The content of this talk will be like this. I'll start with the objectives and background of these studies, and firstly present the results on the gilthead seabream, and then the European seabass, and finish with the conclusions and recommendations. So, why study the genetics of lipids in fish? Well, lipids are important for production efficiency, health, and product quality, as Anna introduced earlier today. For example, excessive lipid deposition in viscera is considered production loss. So we have looked at the genetic effects on these traits and the genetic relationships between the different lipid-related traits. Knowledge that's essential for considering implementation of these traits in selective breeding programs. So I'll talk about fatty acids in this presentation. So I'll start with a short introduction to the most relevant ones. You don't have to memorize this, I will guide you through it. So both seabream and seabass are important nutritional sources of the health-promoting omega-3 fatty acids, EPA and DHA, in the Mediterranean diet. Now, there are several factors that influence the fatty acid composition of fish fillets and other tissues. And the feed is the major factor here, where plant and marine ingredients contribute with different fatty acids. In plant oils, we find high amounts of the 18 carbon fatty acids. And fish oil is the main source of the healthy long-chain omega-3s, EPA and DHA. Now, metabolic factors also influence the fatty acid composition. I'll mention factors like the retention of specific fatty acids, fat oxidation. Fish can also synthesize fatty acids through lipogenesis, which produces these shorter chain fatty acids. And some fish species can convert the shorter chain ALA into the DHA. Now, studies in other fish species have revealed a genetic component to the omega-3 levels of fish fillets, but the genetic parameters of fatty acid composition traits had not yet been explored in seabass and seabream, and that is part of the work that we've done. So let's start with the gilthead seabream, where we studied 967 fish that were commercially produced by Galaxy. All the fish were genotyped with the medfish SNP chip, and approximately 27,000 SNPs, paused filters, and quality control. Now, body weight and visceral weight was reported on all the fish. Viscera is considered or at least one of the main lipid storage sites in gilthead seabream, and here we used viscera in percentage of body weight as an indicator of amount of visceral fats. And for 232 of these fish, muscle samples were chemically analyzed for muscle fat and fatty acid content. So we see here that the size and muscle fat level were normal for commercially produced harvest-site seabream. And these traits also showed large variation. And on this black table, we see that they were also significantly heritable. And looking at the visceral percentage, this had especially high heritability. And assuming that this represents the amount of fat in viscera, this is a highly relevant and interesting traits regarding selective breeding programs. Now, the fatty acid composition of muscle. And this was recorded as both the proportional content and quantitative content. And here you see the main fatty acids in muscle plus EPA and ALA. And you see that the average content of EPA plus DHA was around 800 milligrams per 100 grams of filler. And comparing this to the recommended daily intake, we see that the seabream is a good source of these essential fatty acids for us humans. Now the variation in quantitative content was large, but it only reflected the variation in muscle fat content. So from here on, I will only discuss the proportional content of fatty acids. So here are the heritabilities. We see variation among the different fatty acids, with this 16 carbon fatty acids having the highest heritability. And because this fatty acid is mainly a product of lipogenesis, so new synthesis of fats, this indicates that the metabolic process of lipogenesis is a highly heritable in the muscle of seabream. And we see that both DHA and EPA show moderate to high heritabilities, which means that it's possible to increase the content of these fatty acids through selective breeding. Now we have the genetic correlations between traits. As you see, the standard errors in these estimates are quite high due to the small data sets, but they give us some indications on the relationships between traits. And first, here we see that an indication that body weight and muscle fat are independent of each other, which would mean that we can include muscle fat in breeding programs without compromising on growth. It also seems like both EPA and DHA are independent of body weight. And now, looking at the correlations between the fatty acids, we see that if we choose to select for increased DHA, we would also get higher amounts of EPA and lower amounts of this main omega-6 fatty acid, as well as the main saturated fatty acid in muscle, which implies that there's a potential to select for an overall and healthier fatty acid profile in the muscle. That was the seabream. Now on to the seabass results. Here we have the seabass from cosmetics, which were produced commercially, with an average body weight of 346 grams. And the fish were genotyped with the medfish snip chip and 21,000 snips past filters and quality control. And because the liver is a major lipid storage site in sea bass, we focus on the liver in addition to muscle. And here we measure the lipid and fatty acid content of the muscle of 313 fish, and for 87 of these fish, we do the same on liver tissue. And here we see the fatty acid content of sea bass muscle, and the same main fatty acids as we found in seabream, and with an average muscle fat content of 9%, the EPA plus DHA content is 900 milligrams of filler. And so we wanted to compare muscle fat and liver fat. So first, looking at this plot here, muscle fat against liver fat, we see that there was actually a very low correlation, indicating that there's an independent regulation of the two lipid deposits. And this was further supported by the differences in heritability between the two tissues. Muscle fat had a high heritability, while the estimate for liver fat was much lower. And we see here the heritabilities for different omega-3 related traits. Some of them were high for both tissues, like DHA, but other varied. Now I want to mention this omega-3 and to omega-6 ratio. And the heritability for this trait was rather high in the muscle, which indicates that there's a substantial potential to improve the fatty acid profile of fish fillets through selective breeding by increasing the ratio of these anti-inflammatory omega-3 fatty acids to the pro-inflammatory omega-6 fatty acids. And this is desirable in a public health perspective, as it has been linked to reducing the risk of many of the common chronic diseases. And so omega-3 bioconversion. This is when the animal itself converts the shorter chain omega-3 into DHA, which is, and so the DHA to ALA ratio can be seen as a marker of omega-3 bioconversion. Now, it is assumed that marine species have very low capacity of omega-3 bioconversion. Now, let's look at the data on seabass. Here I have plotted the muscle DHA content to the liver DHA to ALA ratio. And we see a quite high positive correlation, which could indicate that as DHA is produced in the liver, it gets deposited in the muscle. And both of these traits had a high heritability above 0.4. And looking at the fatty acid content, we see that the amount of DHA, the proportional content of DHA found in muscle and liver was much higher than what was given in the feed, while the opposite was the case for ALA. So these results may imply that European seabass has an omega-3 bioconversion activity in the liver that has a strong genetic component to it, and that could impact the DHA content of muscle. And finally, we have done genome-wide association studies for these traits. And a GWAS shows where on the genome there is genetic variation that's associated with the variation in the trait. So these Manhattan plots show the position on the genome of each SNP, and the y-axis here is the significance value of the association. So due to the low number of animals, we should be careful to interpret these results. But what was interesting was that we found a signal on the same linkage group for several of the traits and across muscle and liver tissue. And although these traits do not have the exact same type of significant SNP, some are in the same region. And in this region, we found a gene, and there's a very strong kind of gene. It's PPAR alpha, which is central in the regulation of several genes involved in lipid metabolism, and that has been linked with the omega-3 fatty acid in several studies. Yes, and to conclude, this work has provided key information for implementation of lipid-related traits in selective breeding programs of seabream and seabass. And for the first time, the genetic parameters of muscle fatty acid composition have been estimated in these species. So for seabream, we saw that muscle fat had moderate heritability, and the genetic variation in these traits seem to be independent of body weight. Selective breeding is a promising tool for increasing EPA and DHA in fillets of seabream, and there's a potential to select for a healthier overall fatty acid profiles in the fillets. So for seabass, we saw differences in genetic parameters between liver and muscle tissues that likely reflect differences in their lipid metabolism. There's a substantial potential to increase DHA content of seabass fillets through selective breeding, and the results also suggest omega-3 bioconversion activity in livers that has a strong genetic component linked to the DHA content of fillets. Then there was also signals on linkage group X for omega-3 traits across tissues that implicate the dependent gene PPAR alpha. Thank you all for listening, and thanks to the contributors and partners.